Good morning, everyone. I welcome all the participants for the last day of 6-day faculty development program on emerging trends in sustainable manufacturing, advanced material and additive technologies. Today's our session speaker is Dr. Rajesh Kumar L, Professor from the Department of Mechanical Engineering, Alliance University, Bangalore. Before starting the session, I would like to give a brief introduction about our guest speaker. Dr. Rajesh Kumar is currently working as professor in Alliance University, Bangalore, India. His research interests include polymer biocomposites, biofibers and biofillers and testing characterization of fibers and composite. He is an editor for 7 books published in Elsevier. He has published more than 100 research articles in Web of Science and 33 in Q1 Quarantine and 30 in Q2 journals, including of 54 international and national conference and Scopus Indexed journal. He has been editor for 47 books with reputed international publisher. 7 of them were WOS articles, have been recognized as most cited paper during the year of 2021 to 24. Dr. Rajesh Kumar sir has been listed as the top 2 scientists in the world according to list released by Stanford University, USA and Elsevier from the year 2023 onwards. He is an editor of Scientific Report, Natural Portfolio Journal, EBM for Current Material Science Engineering, reviewer editor for Journal of Thermal Engineering and Energy System, and he is reviewer for more than 7 reputed international journals and 5 national conferences. On behalf of Tech, Multitech, Dr. Rangarajan, Dr. Sakuntala Engineering College and Department of Mechanical Engineering, I would like to give a warm welcome to our guest speaker, Dr. Rajesh Kumar sir. Sir, thank you, sir, for accepting our invitation. You can start your presentation, sir. Thank you, sir.
Yeah, very good morning to all the participants present here. And I would like to thank organizers of this FTP for giving me an opportunity to share my research ideas. Hope I'm audible to everyone.
Sir?
Yes, am I audible, sir?
Sir, you are audible, sir. You can share your screen, sir. No, no.
Yes, hope my screen is also visible. Yeah. Once again, warm greetings to all the academicians and researchers and faculty members present in this August forum. So, the topic of discussion today pertains to research advancements in natural fiber composites, and I'm working in natural fiber composites for the past 8 years. So, I would like to share with you a few insights regarding composite materials, fiber reinforced composite materials, and natural fiber reinforced composite materials, and what are all the research trends which are currently ongoing in terms of natural fiber composite materials, and what are the areas which we can give utmost concentration while we are working on composite materials. So, to be very fundamental, this we all know very well, but however, it is my duty to start from the scratch. Composite material is generally a material system with 2 or more insoluble phases, which are chemically distinct, and these material has to be compatible with each other when they are being mixed together, so that when they are compatible with each other, they produce a synergetic effect, which enhances the strength of one or more materials. One material will have its own strength, while the other material will have its own advantages. Whenever two or more materials are combined together with their individual strengths, all their positives are expected to aggregate together, so that we'll get a material with better strength. So as we know, sandwich is the best example of composite material. It is having its own nutritional value. All greens, cheese, meat, everything which are aggregated together will have its own nutritional value. So entirely, sandwich will have its own nutritional value. Likewise, composite material, when many individual constituents are being mixed together, with suitable processing techniques and with suitable compatibility ideas, they will render material of better strength. So this is the ideology of developing composite material. So the main advantage of any composite material is its specific strength and specific stiffness. Since the materials are expected to possess very minimum density and as maximum strength as possible, its specific strength is expected to be very high, and it is obviously very high as far as many research results are concerned. And its specific stiffness, that is stiffness to weight ratio, is also very high. And their other properties such as fatigue strength, toughness are also very high when compared with a few monolithic metals, not alloys or compounds, monolithic metals. And the main advantage of any fiber reinforced composites is it is devoid of corrosion. So corrosion will not be an integral part as far as any fiber reinforced composite is concerned. So unlike any other metallic materials or monolithic materials, composite materials will not experience corrosion. So these are some few standalone applications of composite materials, and their application prospects are growing day by day. Since the research on composite materials are getting deeper and deeper, the application prospects are getting deeper day by day. And since the processing techniques or the material novelty or their process parameters are getting more and more research prospects, the applications of composite materials are getting deeper day by day. Sorry. Usually, a composite material will have two phases, as we all know very clearly. One is a matrix phase, the other is a reinforcement phase, or a primary phase and the secondary phase. So where a primary phase is of higher volume and the secondary phase is of a lower volume, the primary phase is actually the functions to incorporate the secondary phase within it, and the primary phase is characterized with the low density and good shear properties, whereas the secondary phase will have high strength, high stiffness, and obviously low density. When low density material combines with the low density material, we will get another low density material. And you can see the properties of both the constituents of a composite material are aggregated together to form a very better performing composite material. Usually the primary phase holds the embedded phase that forms the bulk part, and in most cases matrix will have a low strength whose strength has to be enhanced by a secondary phase material, but however its bonding strength is very high. It is usually corrosion resistant. The corrosion resistance of the composite material is incorporated by the matrix material alone. Rather, a reinforcement material may also not be corrosion prone, but however, majorly the corrosion resistance is imparted to the composite material through a matrix material. Whereas the reinforcement particle is of lower volume, it is reinforced in lower quantities in the matrix material. They are mixed together to form a composite material like steel and concrete. The suitable processing techniques are being used to form a laminated or fiber reinforced composite material. Mostly the secondary phase will have various forms such as fibers, particles, and flakes. This interface forms a region. Interfacial properties of any composite material is very, very important since both the constituent phases of the composites are chemically distinct. They should form an interface where the interfacial strength of any composite material determines its ultimate strength. That is why, as previously mentioned, the compatibility between the secondary and the primary phase plays a major role in forming the interface of any composite material. So, whenever a composite material has to be a high performance composite material, or it has to be an efficient composite material, its interface has to be as better as possible, as maximum better as possible, so that the interfacial compatibility between the primary phase and the secondary phase is better and the composite material results with higher strength. So these are the basic classification of composite material. Based on matrix, we have 3 classifications, and based on reinforcements, we have another 3 classifications. These are very common. And as far as any composite material is concerned, a composite can be designed based on various factors. Either it can be designed based on the concentration, that is either the volume fraction or the weight fraction of any material, or the size of the reinforcement, macro, micro, or nano. Recently, macro reinforcements are literally dipping down, whereas micro and nano are getting more and more visibility. And the shape of the reinforcement, as we have mentioned, fibers, rather than reinforcing long fibers, short fibers are being reinforced recently in many composite materials, and flakes and whiskers were also preferred, so that the area which they occupy, the specific area which they occupy, becomes lesser, so that the load transfer is higher, and the composite material will have a better strength when the shape of the reinforcement is varied, and the spatial distribution, either unidirectional, bidirectional, or random orientation as far as fiber reinforced composite is concerned, it is being another factor by which a composite material can be designed, and the orientation with respect to the axis, with respect to the loading direction. Whenever the loading direction varies, the orientation of the secondary phase can also be varied, so that in that particular direction, the load bearing capacity of the composite material is better. And usually there are natural and synthetic fibers in existence, and the synthetic fibers are being derived from non-natural sources. So in order to counter that particular disadvantage of being a synthetic fiber, natural fiber is being used to reinforce the matrix material, a plastic, a thermosetting or thermoplastic material. Even though the natural fibers will have comparatively lesser strength when compared with the synthetic fibers, they have their own application areas, and due to their sustainability, biodegradability, and renewability, natural fibers are mostly preferred in the current scenario. And even though they are used only in low or medium density applications, their applicability shows a wider improvement due to various advantages of those natural fibers. Even the cost of processing, the processing method of the natural fibers are comparatively lesser than the synthetic fibers. So these natural fibers have become the center of attraction for many researchers, and various research works in various prospects are being undertaken as far as natural fibers are concerned. Natural fibers can be used in various applications based on their origin, and some of the examples of natural fibers include jute and hemp. And we'll also see what are the classification of natural fibers. Various plant parts, the natural fibers are derived from various plant parts. Not only plant sources, but animal and mineral sources are also the sources of natural fibers. So natural fibers means they don't mean only the plant-based sourced natural fibers, but also animal And we know in most of the cases, animal fibers are also used as reinforcements. And recently, humans are also the source of natural fibers like keratin. Keratin is the best source of natural fiber. Hair fibers are being researched in many cases as short fibers. So natural fibers are derived from natural renewable based sources. So some of the common methods of manufacturing metal matrix and ceramic matrix composites are listed here. And however, we are interested in manufacturing of polymer matrix composites. There are four major methods of manufacturing polymer matrix composites. The main objective of all these methods is to develop a proper interface between the matrix and the reinforcement so that the interfacial strength of the composite material increases, ultimately resulting in the maximum strength of any composite material that is being developed. And most commonly used methods are hand layup method and progressively compression molding method, vacuum bagging method. And recently, additive manufacturing is a very highly emerging area, whereas most of the researchers are oriented towards additive manufacturing methods to have better publishability of papers. So hand layup is a very simple and oldest method of manufacturing composite materials. These are completely manual, and the fibers are being reinforced layer by layer, and over which a layer of resin is being coated, and the final part is being trimmed off. Next is spray layup, which is more like the hand layup method, whereas rather than reinforcing or rather than placing the layer by layers, they are both the layers or both the phases are being sprayed together on a mold, and finally they are being cured and being used further. Vacuum bagging is specifically used for woven type natural fibers. When the fibers are being used in the form of a mats, vacuum bagging can be used, whereas this particular method cannot be used for short fibers or viscose, and even for fillers this cannot be used since the vacuum pump may be clogged. So vacuum bagging is another type of composite manufacturing method, which is an intact manufacturing method. The composite material which is being resulting from vacuum bagging will have a better interface when compared with other methods other than compression molding. Rather, compression molding is another technique, which is the advancement of hand layup, where the pressure and the temperature is being applied in the form of automatic machines. Now, pressure and temperature can be controlled through suitable gauges, whereas it contains another upper mold and lower mold, where in hand layup everything is being manual, whereas composite molding, whenever we place the laminates within the mold, the pressure and temperature control will take care of the cure. So composite molding is a very major method of manufacturing of composite material these days. When the composite molding machine is not available, researchers may opt for hand layup. Next is transfer molding. This is a very least used technique. However, this was in existence previously. And transfer molding and injection molding are more alike. These are specifically used for thermosetting composite materials. Rather, injection molding is also used for large quantity production with low cost. A mold is being injected with the contents of the composites and cured, and the mold is being taken out with the final casting. And the most highly emerging technique is the additive manufacturing or 3D printing of composite materials. Actually, the research trend is in the transformative stage as far as additive manufacturing is concerned. So far, all the methods are analog, whereas this particular method of manufacturing composite material is purely a digital composite material, whereas the material may be removed previously in all the previous cases whenever final shape of the product has to be obtained, whereas in additive manufacturing, directly the final shape of the product is being obtained through adding of adding of materials with the predetermined model of the product. So the model is being generated using any modeling software. It is being sliced layer by layer, and additive manufacturing is a technique where layer by layer product is being built up and the layer by layer assembly is finally cured to form the final product. So this specifically shows the schematic of the additive manufacturing method, specifically where the material comes out and the platform over which the composite is being built, and we can see the layer by layer build of the products, and finally the support structures are being reported. Support structures are integral part of additive manufacturing methods, where in order to avoid the distortion of the final material, whenever the lengths and breadths of the composite, length and breadths of the printed parts are being very high, supports are being given and the support structures are being removed, and finally this material is cured to form a final product. However, the strength of the final 3D printed product is on par with the products which are being on par with the composites which are being built through other methods. Currently the major research works focuses on reinforcing either the particles or short fibers with the plastic materials and forming a filaments, and only the filaments are being given as an input to the additive manufacturing machine or the 3D printer, and those filaments contain the matrix and reinforcing materials, and the final composite which is being printed in a 3D printer will contain the natural fibers which are directly embedded into the filaments. And most commonly used methods of additive manufacturing are fused filament fabrication, SLA, selective laser sintering, direct writing, and binder jetting. The main advantage of the additive manufactured parts are the manufacturing of intricate shapes in one shot, and the complex parts can be easily built using additive manufacturing, whereas the main disadvantage of any additive manufacturing method is the time consumed and the material which is being used and the incompatibility in using the material in developing the filament material. Though there are many techniques to develop specific natural fiber reinforced filaments, the strength of the proprietary material printed product with the natural fiber reinforced product can be easily compared, and the natural fiber reinforced product will have comparatively slightly lesser strength when compared with the product which is being printed with the proprietary material, which needs more research focus, and currently researchers are going on. Even whenever the filaments are being developed, it is also considered to be the reinforced product, where whenever the interface between the filament and the thermoplastic and reinforced material will not have better compatibility, they may not be compatible even after printing. So the interfacial compatibility between the reinforcement and the matrix during the development of filament itself is important before even being printed. So the most commonly used method of additive manufacturing is the fused deposition modeling, since it consumes lesser material, and the setup of this particular technique is very easy when compared with the other methods, and the reinforcement of the fibers within the matrix material can be accommodated better in fused deposition modeling comparatively. So the filaments are being melted, extruded through a nozzle, and are deposited through a platform where the layer by layer build of the final products are being done, and finally the additive manufactured part or the 3D printed part emerges. Most of the process parameters, including the deposition speed, filament feed rate, nozzle diameter, width, head temperature, plays a major role as far as the final product is concerned. Shrinkage compensation and the appropriate deposition strategies are very much important to develop accurate parts. And deposition of multiple materials is also possible, whereas this once again needs a serious research. Hybrid materials are having least scope as far as additive manufacturing methods are concerned. This shows the schematic of a fused deposition modeling. Support material and built material are being fed separately into a nozzle, and whenever the model identifies itself to a supporting material, the support material is being added, and whenever it is the built material that is being identified in the STL file, the built material is being added. So this shows the process parameters as far as additive manufacturing is concerned. The line count, the top layers and the bottom layers, wall thickness, infill density, layer height, bed temperature, nozzle temperature, and printing speed. These are the major processing parameters that can be set as far as additive manufacturing methods are concerned. Very specifically, wall thickness, infill density, bed temperature, nozzle temperature, and printing speed majorly influences the quality of the final printed parts. And the diagram on the right side denotes the various infill patterns which can be used for the 3D printing of specimens, and various researches have been made in comparing these infill patterns with the honeycomb pattern. We know very well that the most specific, the pattern which possesses most highest specific strength is the honeycomb pattern, which is being used in sandwich materials. And the additive manufacturing method, I mean the infill patterns which are being used can be easily compared with the honeycomb structure, so that the specific strength of any material is high. Specific strength of any 3D printed material is very high, and there are 14 infill patterns, and most of these infill patterns will possess close strength with the honeycomb structures. So the infill pattern variation is also another prospect of research where the strength of the 3D printed part can easily be compared with the honeycomb structures. And the properties of the composite materials which are mostly evaluated. Whenever a composite material is evaluated for its property, or in most cases there is a hopes that the composite material which are developed has to be measured for all the properties, which is not actually the case. A composite material is developed for a specific application. There will be a specific application for which the composite material, specifically the natural fiber composite materials, are developed, and only the properties which are warranted with applications has to be measured, so that the composite material will specifically serve its purpose. Rather than measuring all the properties, the application oriented properties are to be measured for any composite material which will be most suitable for a developed material. Rather, there are mostly various properties that includes thermal properties, mechanical properties, tribological properties, machinabilities, physical properties, and biodegradability properties. And whereas these biodegradabilities are specifically applicable only to the natural fiber composite materials. The natural fiber composite materials will have their own micro constituents like cellulose, hemicellulose, lignin, pectin, wax, and other materials, which influences the mechanical properties of any natural fibers. Rather, not only mechanical properties, these micro constituents influence the properties of the natural fibers, which are being incorporated, which in turn imparts its own properties to the final composite material in which it is reinforced. So mechanical properties are majorly influenced by the crystallinity of cellulose, rather non-crystallinity of the cellulose in few cases, and the combined amount of hemicellulose and lignin, and even the presence of lignin. So whenever mechanical properties are to be measured, the material needs higher hardness. So higher crystalline materials are highly hard and brittle materials. Whenever and whereas the matrix material is ductile, whenever a brittle material is reinforced within a ductile material, obviously the strength of the final composite material is going to be improved. And coming to the moisture absorption, rather they are being governed by the presence of hemicellulose, non-crystalline cellulose, lignin, and crystalline cellulose. And thermal degradation is influenced by the absence of hemicellulose, presence of cellulose, and a partial presence of lignin. Whereas biological degradation, the presence of all the micro constituents, So these are the influence of mind. So that is why whenever any natural fiber is being identified by any researcher, or they are being planning to be used as reinforcement in a matrix material, the measurement of micro constituent of a natural fiber is very important. So whenever this idea is being obtained and this idea is being generated, when the idea of the micro constituents are being got, then the prospect of reinforcing or prospect of using the material, that particular natural fiber as reinforcement is very clear. Whenever the micro constituents are not in the required or not in the expected quantities, then the natural fiber will have the least prospect of being used as reinforcement in the natural fiber. The most researched, the mechanical properties are the most determined properties as far as natural fiber composites are concerned. So we are dealing with the properties other than those mechanical properties, since they are being most researched properties and almost they are being saturated. So tribological properties can be evaluated for any natural fiber composite for their application in either contact or brushing applications. So that the assessment of wear and frictional behavior under various loading conditions, under various process parameters can be made as far as the natural fiber composites are concerned. And as we know, we might have gone through many research papers, and many research papers are focusing on optimizing the process parameters for any natural fiber composite material when they are subjected to tribological analysis. And recently many research papers are being detailing the use of the natural fiber composite materials as the automotive friction components also. So tribological properties are one such properties which have higher prospects as far as natural fiber composites are concerned. So these material-based factors like composite configuration, nature of the fibers, fiber alignment, and other machine-based factors such as applied load, sliding speed, and temperature, sliding velocity type of wear mechanism can also be used for amazing the wear behavior or tribological properties of any composite material. Most of the researchers focus on type of wear testing and type of environment. Added to this, the temperature and the application of the composite material. Rather, it is very clear as far as tribological properties are concerned that whenever tribological properties are measured, it indirectly means that those composite materials can be readily applied in contact applications. So these are some of the insights regarding the tribological properties of the composite materials. The morphological analysis plays a major role as far as the composite materials are subjected to tribological properties, and many inferences like the compatibility, the fiber and matrix adhesion can be drawn from the morphological analysis. And whereas the pin-on disc and ball-on disc are the major tribological property, the major methods of measuring tribological properties. And next most researched property is the machinability property. Like drilling, milling, and turning, the composite material is subjected to various machining operations, and the behavior of the natural fiber composites for the machinability for against these machining operations are being analyzed, and the inferences are being drawn against those cutting parameters. And we know that most of the composite materials are not directly applied in final applications. They will be subjected to a suitable machining operation. So that is why these machinability analysis plays a major role. And various prospects of subjecting the natural fiber composites to various machining operations are being shown in this particular slide. Applications demand the machinability analysis, whereas the milling and grinding operations are having higher prospects rather than drilling. Drilling and turning were the most researched machining operations, whereas milling and grinding are the least researched operations. Researchers who are into the machinability analysis of natural fiber composite materials may focus on machining and drilling. Apart from this, many non-traditional machining are also being done in most of the cases, like non-traditional machining operations like abrasive jet machining, water jet machining are being used for the analysis, are used to assess the behavior of natural fiber composite materials, since those are non-contact type machinings. And here also morphology of any composite material plays a major role in determining the behavior of the natural fiber composite material against any of the machining operations. The next most researched property is the thermal property, and which is the most important property as far as any composite material is concerned. Whenever the natural fiber composite materials are being applied at high temperature applications, the determination of thermal properties plays a major role. As we have seen earlier, the thermal stability, crystallization kinetics, the behavior of the composite material against thermal and mechanical, combined thermal and mechanical loads are being researched, are being analyzed. And whereas flammability is also another important parameter. Whenever the composite material is expected to be a fire resistant or a flame resistant material, the flammability behavior of a composite material is also to be analyzed. Thermogravimetric analysis assess the thermal stability of any composite material. A composite material is being subjected to rise in temperature, and the behavior of the composite material with respect to time and the temperature rise is being plotted, and the plot is being used to assess the thermal stability of any natural fiber composite material. And the differential scanning calorimetry is used to analyze the phase transition of any composite material against time and temperature. And flammability analysis is used to determine the flame retardance or the fire resistance of any composite material. That is, when the material is being ignited, how long the material withstands the fire is the assessment criteria as far as flammability analysis is concerned. And the limited oxygen index determines the ability of the material to undergo combustion is being evaluated through limited oxygen. Apart from this, heat deflection temperature is also another common method of testing of any composite material. I'm sorry. Next is the biodegradability analysis of any composite material. This property is specifically applied only to the natural fiber composites. This cannot be evaluated for any synthetic fiber composite material, since they are not breathable. Only natural fiber composite materials are breathable and biodegradable. There are various methods of determining the biodegradability of any composite material. Either it can be a soil burial test, or it can be a compost, or it can be a landfill test of any sort. And whenever the material is being biodegradable, and whenever the service, after the service life of the composite, the disposal, during the disposal of the composite material, the biodegradation plays a major role, which cannot pollute which should not actually pollute the environment. So for evaluating that particular property, biodegradability analysis is very much important as far as natural fiber composites are concerned, and how far they are biodegradable and how far the service life of the natural fiber composite material are extended are the major results which we obtain using the biodegradability analysis. And there are many researches which are going on end of life cycle. See, every composite material will have its end of life. So after the end of life, after the ending of the service life of any composite material, this biodegradation plays a major role. So either composite material will be discarded, or the composite material will be recycled. Only these two aspects are possible after the service life of any composite material. So whenever the composite material is being recycled, various methods of recycling involves chemical, thermal, and mechanical recycling. And whenever the composite material is being discarded, they are being discarded through soil burial, through composting, through digestion, or through landfill to mineralize the natural fiber composite material. Synthetic fiber composite material will not undergo mineralization, whereas only natural fiber composites undergo mineralization. So they are being ingested by the enzymes. They are being converted into useful products whenever they are being discarded in the soil. So these materials are soil-friendly materials. And whenever the composite material is being recycled, they are again developed into a product. They again enter into the service life. Whenever the composite material is being discarded, they act as a manure. The soil, they enrich the soil again. Plants are being grown, and natural fibers are being obtained once again from those materials. Once again, they form products, and this continues. This cycle continues all together, so that the service life of the product begins at the bottom and the end of the life begins at the top. So natural fiber composite materials are very environmental friendly in such a way that in any form, when they are being either reutilized or they are being discarded, they are again supporting the formation of useful products. So the valorization as far as natural fiber composite materials is very high when compared with the synthetic fiber composite materials. And another important property which is being analyzed for the composite materials are the weathering or durability analysis. This can be determined for synthetic and natural fiber, but however, the durability analysis is very much needed for the natural fiber composite materials to subject them to the outdoor environmental conditions during their service life. And maybe whenever the composite material is being formed as a product, the product may not be used in a closed environment, it may be used in an open environment, and the open environment will be subject to all possible environmental conditions. So while even developing the product itself, before even developing the product, the composite material has to be subjected to weathering or durability analysis, so that the durability of the material can be assessed in any environmental condition possible. And by the durability analysis is being done in two different factors. By the environment, either mechanical weathering or chemical weathering is done. Maybe it may be subjected to chemical weathering or mechanical weathering, and through testing conditions, either it will be used in open environmental conditions without any add-ons. It will be put up in the open environment, and the weathering of the weathering behavior of the natural fiber composite in the natural conditions are being assessed. Even there is another condition called accelerated weathering. The simulation of the natural conditions is being done in a condensed period of time, and the weathering behavior of natural fiber composite material under accelerated conditions are also being done to evaluate their durability. So various factors involving weathering are one, the air is the major factor for weathering, which induces physical change. And whenever the physical change is being induced in the composite material, surface roughens or the tissues are being removed. Since it is a natural material, tissues are being removed so that the microconstituents deplete, and the depletion of microconstituents change the behavior of the composite material. And moisture is a major factor as far as weathering is concerned. Since most of the natural fibers are hygroscopic, are hydrophilic, the moisture plays a major role in deteriorating the durability of any composite material, whereas sunlight plays another major role. Only these three are the major factors which are to be accounted whenever the durability of a composite material is assessed during the weathering. And usually natural fiber composite materials, in order to obtain higher strength materials, they are being hybridized to form hybrid composites. So hybrid composites will have still further advantages when compared with the natural fiber composite, individual natural fiber composite materials. So the definition of a composite material remains here as it is, whereas the secondary phase or two or more phases are used as reinforcement, so that they forms hybrid composites. And here also the major factor which is to be concerned is the compatibility between the two secondary phases. So it is not only sufficient when we measure, it is not only sufficient to assess the compatibility of the natural fiber composite, the matrix phase with the reinforcement phase in the individual, but whereas in hybrid, it is also important to measure the compatibility between two secondary phases, so that they do not pull down the advantage of a matrix material. So they aggregate to the advantage of a matrix material and finally result in very high strength composites. So hybrid composites vary. Their secondary phase vary in between micro to millimeter scales. and the microscopic reinforcements are more homogeneous, so that whenever the individual fibers are allowed reinforced, they form voids, whereas when fillers are being used as hybrid reinforcements, they fill up the gaps in the voids, so that the voids do not act as a stress concentration zones and bringing down the final strength of the composite material. In hybrid composite material, the strength of the composite material obviously increases. So one classic example of, or one classic representation of a hybrid material is graphene platelets are being used in polymer matrix and forms the graphene platelet reinforced polymer matrix composite. And whenever one more particle or one more additional hybrid reinforcement and fiber is being used as a hybridization strategy to a modified matrix material, then graphene platelet and particle reinforced hybrid composite emerges. In other case, whenever fibers are short fibers or critical length fibers are being used as reinforcement, graphene platelets and fiber reinforced composite materials are emerges as hybrid composite materials. Some of the design variations of hybrids are being shown. Either the hybrid, the secondary reinforcement can be homogeneously dispersed, or they can be alternatively placed. And whenever there are two or more reinforcements, the stacking sequence in C, stacking sequence can be varied, or in D, the sandwich composite material can be used, or they can be used alternatively. Either they can be alternatively sandwiched in clusters, so that the hybrid composite material specifically applies to any one specific application. And the hybrid materials are majorly classified based on two factors. One factor is based on the functions, the other factor based on the bond strength. The functional classification renders three composite materials, three hybrid composite materials: structurally hybrid materials, functionally hybrid materials, and chemically bound hybrid materials. Whereas as far as bond strength is concerned, the class 1 and class 2 hybrids are emerging. So class 1 hybrid materials show weak interactions between the two phases, whereas class 2 hybrid materials show strong chemical interactions such as covalent bonds. So whenever the compatibility is being measured for the secondary phases, only the secondary phases which have the ability or the potential to form covalent bonds are being preferred mostly, so that class 2 hybrid materials emerges, which renders a strong chemically interactive composite materials with better strength. So some of the advantages of hybrid materials are they have specific optical, electronic, and magnetic properties when compared with the individual fiber reinforced composite materials or individual polymer matrices. And rather than the solid state inorganic materials, hybrid materials show more polymer-like handling because of their large organic content or the formation of cross-linked inorganic networks with the small molecular precursors, so that the polymerization reactions are very swiftly formed, so that they form high-strength hybrid composite materials. Some of the applications of hybrid composite materials include scratch-resistant coatings, electronic applications, fire-resistant hybrid materials. Whenever a fire-resistant material is to be developed, one natural material with one synthetic material can be used, like natural filler can be used as a fire retardant material, and aluminum, one more synthetic filler like aluminum phosphate or boron carbide can be used as fire resistant filler, so that the composite material, the fire resistance of the composite material increases further when compared to the usual composite materials. And they can also be used as dental filling materials, they can be used as electrolyte materials, and obviously they can be used as corrosion protection materials. Next class of materials, as far as the natural fiber reinforced materials concerned, are the nanomaterials or nanocomposites. So materials which we have dealt so far are in micro scale, and next will be the materials which are being dealt in nanoscale. So as we know, whenever a nano-sized particle is the constituent of any composite material, we call it as a nanocomposite. And whenever the nanomaterials are being used in polymer matrices, they are specifically called polymer nanocomposites. And polymer nanocomposites will experience drastic improvement in properties, since the specific area occupied by the nanoparticles is very high, the stress concentration zones are very less when compared with the fiber reinforced or the hybrid composite materials. And some forms of nanomaterials which can be reinforced are nanoparticles, nanorods, or nanofibers, and nanotubes, specifically carbon nanotubes or halogene nanotubes. These are the materials which prospectively can be reinforced in any these are the most secondary phases in nanoscale which can be used in a polymer matrix. So some of the polymer nanocomposites include, the variations of nanocomposites include shape of the reinforcement, as we have seen: fibers, rods, fillers, tubes, and flakes. They are used, and dispersion mechanism is another variation of a nanocomposite, and morphology of any nanomaterial reinforced polymer matrix is another variation of a polymer nanocomposite. And whenever the external stimulus is another factor in developing a nanocomposite, that that forms another variation of a polymer nanocomposite. Each and every nanocomposite will have their own strengths and weaknesses, and mostly they possess very minimum weaknesses when compared with the strength of nanocomposites. And these polymer nanocomposites are currently polymer nanocomposites are used or developed based on bio-inspired concepts. So whenever the nanocomposites are being developed using bio-inspired concepts, they have a very good dispersion of the nanomaterials within the matrices. Their structures are found to be aligned, and the content of the reinforcement is found to be as high as possible. So whenever the content of the reinforcement is found to be as high as possible, the strength of the composite is very high, and the interface is very important as far as nanocomposites are concerned. The interface is tailorable. Whereas whenever the nanocomposites are manufactured using traditional methods, they have very low strength due to the poor dispersion, and the dispersion structure is very random, and more content cannot be used due to agglomeration. Whenever nanocomposites are used, agglomeration is a very major issue when the suitable processing technique is not being used, and the interface cannot be tailored as far as the traditional method is concerned. So polymer nanocomposites has to be developed based on bio-inspired methods, so that the advantages are very high when compared with the traditional methods. So some of the types of nanocomposites include hybrid nanocomposites, including natural nanomaterials like collagen, and natural or synthetic polymers with another ceramic nanoparticles. So since the natural polymers are being used with ceramic particles, ceramic nanoparticles, they form polymer nanocomposites with higher strength, and usage of hydrogels and aerogels as the reinforcement material in polymer matrix, and usage of nanocomposites, the cellulose based materials in nanocomposites, like developing cellulose or nanocellulose based nanocomposite materials. These are some of the variations in nanocomposite materials. And the application of nanocomposites have a very wide spectrum. They can be used in cables. Very specifically, they are used in energy storages, biomedical applications, sensor-based applications, and EMI shielding applications rather than other applications. Due to the presence of nanoparticles, their porosity increases, so that their specific surface area increases. So the energy storage capability of any nanocomposite material is very high, and they can be readily used as EMI shielding applications due to their barrier properties, and they can be used as the biosensors due to their sensing abilities, due to the accommodation of more sensing elements. Their sensing abilities will be very high, and obviously their biomedical applications cannot be described in words, so they have very high very high prospects in biomedical applications due to their renewability and due to their better strength when compared with the synthetic materials. So any nanocomposite material will have the research in all these prospects, and whenever the research in any nanocomposite material is being focused on any of these aspects, they have a good prospect of publication, and they have the good prospect of extending the research to another level. So the properties of nanocomposite materials can be measured very easily. I mean, not very easily. They can be measured in very wide range. So that the developing of a nanocomposite material itself is a very novel aspect as far as any natural fiber composite researches are concerned. And their characterization is another part. Whenever they are characterized using proper characterization methods, their application prospects can be very easily. They can be application prospects can be very easily decided, and the synthesis methods of any nanocomposite can be easily optimized, so that their synthesis method plays a major role in determining the properties of the composite material and the final application. Obviously, whenever the final application is being decided, and based on that the synthesis properties and their characterizations are being done, the nanocomposite will have very good research prospect. Then the prospects of using nanocomposite materials in additive manufacturing is another upcoming research area. Whenever the nanomaterials are used as a hybrid raw material, they offer many advantages like superior mechanical, electrical, thermal, and specific strengths and functional properties when compared with the microscale materials. And whenever suitable methods are being developed to incorporate these nanomaterials in polymers, and those polymers are being used to be converted as a filament, then the additive manufacturing of nanomaterials will become possible. And whenever the additive manufacturing, the 3D printing of nanomaterial based polymers are being used, they have obviously better, they surely will have better strength when compared with natural fiber reinforced composite materials. And these are some of the variations whenever the natural fiber, nanomaterials based composite materials are developed using 3D printing, and whenever hybrid composite materials with fillers and fibers are being used with two different printing heads in one printing platform, they can be used to develop better materials with high strength. And whenever nano rods are being reinforced in polymer matrices, they form another class of composite materials with better strength. But there are many challenges as far as the nano particles or natural fibers are being used as reinforcements for 3D printing applications. Some of the challenges are inherent agglomeration. Whenever there is an agglomeration within the filament itself, the nozzle of the 3D printer gets clogged, so that the material will not flow uniformly, and finally the layer by layer structure distorts, and it gets disturbed, and the final strength during even the final curing, that cannot be eradicated, and the strength of the final 3D printed part will be very, very less, or even possess no strength. It will be just a very brittle structure, which is brittle product which is being developed. And whenever an agglomerated filament is being used, and natural fibers are more prone to moisture, and whenever they are being reinforced in the filament, and whenever they are kept in open environment without using controlled environment printing, they are hydrophilic. So whenever hydrophilic filaments are used, the voids development, the void formation is very high as far as the final product is concerned. And in order to mitigate all these issues, the process parameters and feedstock quality has to be controlled very meticulously, so that the clog deposition heads is being avoided, and the final product is possessing better strength. And in many researchers, it was being quoted that the decrease in lignin content improve most of the properties, and in order to decrease the lignin content, a suitable delignification strategy or suitable fiber treatment strategy has to be employed, which is being very crucial in developing a natural fiber composite material for a natural fiber based polymer material for 3D printing. So these are the common research aspects so far we have discussed, and this particular and the forthcoming discussions are focused on specific research trends which are ongoing currently. So the first research trend is the valorization of biomass. So whenever a waste is being induced, and whenever a waste is being properly identified, whenever they are identified to be polluting the environment through landfills, the valorization of those waste or biomass or the order of the research these days. So converting those waste materials or plant-based or animal-based biomass into useful materials, fuels or chemicals is more prevalent these days. Either they can be used to develop advanced composite materials, or they can be used in developing biofuels, or they can be used in developing biochemicals. So the valorization of biomass is an ongoing research trend. Whenever a prospect is being identified that biomass can be utilized, those are waste. So those agricultural waste will have potential to be developed as materials or fuels. Whenever that is being properly identified and whenever that is being properly materialized, that becomes a very good point of research. And though valorizing those biomass or waste reduces the problem of conventional disposal, and these valorized products are finding applications in various fields like material science, biomedical applications, wastewater treatment and energy storage, for device fabrication like biosensors. And biomass valorization includes the feedstock in 3 different generations. One is the first generation, the second generation and third generation. Feedstocks are being used. These are believed to be. And whenever the first generation feedstocks are used, they include the edible seeds and the starchy seeds. And mostly second generation feedstocks are being used for hope I'm in the meeting and I'm audible. Yeah, let me continue. So the mostly second generation feedstocks are being used mostly in many of the studies, whereas that includes the lignocellulose. That is, for example, whenever a seed or a pulse or lentil is being taken out of, for example, whenever rice is being taken out of the paddy crop, the plant remains waste, remains as an agricultural waste, and developing lignocellulosic fibers from that particular plant is one classic example of valorizing agricultural waste. And even third generation waste, such as utilizing the plant material directly for developing another useful product, is another example of using biomass valorization. So algae is the best example for a third generation biomass or feedstock. So biofuel generation through the cultivation of algae is also another prospect of research whenever third generation biomass feedstocks are concerned. And the next ongoing research trend is the utilization of carbon in natural materials. Whenever the natural materials are being used to develop activated carbon or carbon-based biomass derived carbon-based nanomaterials, that becomes a very high research trending. So the carbon-based materials is widely used despite the complex synthesis or manufacturing methods. They have very complex chemical involving synthesis methods, but however, whenever the carbon is derived from a biological source, it will have high porosity and high surface area, and the utilization of such carbon-based nanomaterials is having very high prospect in energy storage applications like battery supercapacitors and fuel cells due to surface area, porosity and voids. So the developing activated carbon or carbon-based nanomaterials from the biomass is another research trend. And this shows some prospects from where the sources of the nanoporous carbon deriving from the biomass, and the utilization of such nanocarbon biomass in various applications like electrochemical energy storage, batteries and supercapacitors. And the final research trend is the bio-nanocomposite development. And whenever nanocomposites are developed from the biological materials, we call specifically them as bio-nanocomposites. So the nanomaterials derived from sustainable and biodegradable polymers are the most attractive materials. And bio-nanocomposite materials are specific class of materials other than the nanocomposites when they are being combined with the nano-sized fillers, the nano-sized fillers which are derived from the biological sources with the polymeric materials. We specifically call them as bio-nanocomposites. And most commonly used nanofillers include hydroxyapatite and organic or inorganic metal nanoparticles like marlinite clays and nanoclays. And these nanobiocomposites are specifically used majorly in developing biosensors for analyte sensing applications, since they possess high specific sensitivity and wider target spectrum. And biosensors built from bio-nanocomposites are highly selective, rigid, sensitive, and reliable when compared with the sensors which are developed from the synthetic sources. So these are some of my discussion aspects as far as the research trends of natural fiber composites are concerned. The session is open for discussion. If you have any clarification or any aspect which you would like to bring up, I'm open. Arvind sir. Indian discussions are welcome.
Sir, thank you for your presentation, sir.
Thank you, sir. Participants have any queries? I'm ready, sir. I'm ready to.
Yes, sir. Participants, if you have any doubt, please you can post your question. Sir, is there any recent development in natural fiber readily available with additive manufacturing, sir, making that natural fiber into extruder, sir?
Sir, actually, that is the most obvious and most compatible method of developing a natural fiber composite for additive manufacturing application. Only when you use a twin screw extruder to develop a composite material, then the final strength of the 3D printed natural fiber composite material increases. However, another prospective method of developing a filament is yet to be developed. That is a very wide open area of research. Other than twin screw extruder, I don't find any other method of developing natural fiber composite material for 3D printing. If at all this can be taken up as a point of research, you have a very good publishing scopes.
Okay, sir. Sir, is there any possibility for in FDM we can use like cross filler material to send that filler material? Instead of filler material, can we use this natural fiber, sir, for printing the component?
Sir, we have actually tried one work by reinforcing hemp fibers within PLA filaments, but the inherent difficulty in reinforcing the hemp fibers within the PLA filament is that we cannot downsize the hemp fibers. Hemp fibers are available in various lengths. Only we can cut the natural fibers, but we cannot downsize the diameter of the natural fibers. We don't have any suitable method of downsizing the hemp fibers. And whenever those hemp fibers were reinforced using twin screw extruder in PLA filaments, we found lump of hemp fibers here and there. But even though that did not compromise the strength of the final 3D printed material, the suitable processing method of downsizing the natural fibers for reinforcing them or for again using them in twin screw extruder is another area of research which can be easily concentrated on. We are actually working on it, sir. We are working on downsizing the natural fibers to be used as reinforcements in the PLA matrix.
Okay. Yes. Sir, if that is possible, means what could be the post-processing method, sir, to remove the material? Which will be suitable, sir?
So post-processing method to remove which material, sir?
Like natural fibers as reinforcement, if you are using, means there will be any issues, sir, in post-processing? Like removing the metal.
Usually, since the matrix is a very high, PLA is a very high constituent, post-processing will not be, or post-curing or post-processing will not be an issue. But at places we cannot control the layers, we cannot control the layer in which the agglomeration or the lump falls on. So that specific point acts as a stress concentration zone. So we have to maintain as minimum agglomeration as possible whenever the hemp fibers or the natural fibers are being used. Post curing will not be a problem, but printing will be a problem whenever natural fibers are used. That has to be properly controlled.
Okay, sir. Thank you, sir. Participants, if you have any other doubt, you can ask us, sir. Few people were asking about your contact details, sir. We will share in that FDP group itself.
So, sir,
yeah, okay. Slide is there. Yes.
Slide is there. They can note
Participant,
down.
Nagaraman, sir, you can note down, sir. Participant, Nagaraman, sir, you can note down, sir. Sir, I think there is no more questions, sir.
Fine, sir. We'll wind up.
Sir, thank you for your wonderful presentation, sir. In further endeavors, we can collaborate with all kind of these FDPs and research programs, sir.
Sure. I'm ready to. I'm open for collaboration, sir.
Okay.
So thank you all participants for your patience listening. I hope I have taken your valuable time and I have given valuable inputs. So thank you for your patience listening. Thank you one and all. Thank you the organizers for hosting me in a session. Thank you. Best wishes to everyone. Thank you,
sir. Thank you, sir. Thank you, sir.
Best wishes to everyone.
Thank you, sir. Thank you, sir. Thank you, sir. Participants can join for the afternoon session, followed by validity session at 2:15 p.m. Thank you. At 2:15 p.m. Thank you.